Hello, everyone. Welcome to another keynote slash tutorial. And today um, we are talking about NVIDIA's Nsight suites, another tool called Nsight Compute. And today we have NVIDIA expert on this tool, Felix Schmitt. Thanks, Felix, for joining us. Felix is a senior software engineer in NVIDIA developer tool team. He's developing a range of performance analysis and correctness checking tools, including Nsight Compute. Before joining NVIDIA, he was working as a research associate, investigating novel performance analysis tools and techniques. He holds a master's degree in computer science from Dresden University of Technology, Germany. So over to you, Schmitt.
Yeah, thank you very much. Okay, let me try to share my screen. Okay, can you guys see my screen now, my slides?
Yes, we see a brilliant NVIDIA green.
Okay, let me try to make the video a little smaller here. Okay, perfect. As said, my name is Felix Schmitt. I work in the developer tools business unit of NVIDIA, and I'm one of the main developers of this tool called Nsight Compute that I'll be presenting on today. There were a couple of other contributors to these slides as well, so I named them there, Mahen and Jonathan. Okay, so where is Nsight Compute in this Nsight product family? It's kind of the second step often if you do compute analysis or CUDA analysis, for example. You would normally start with Nsight Systems to get the whole picture analysis of your application or your platform. If you have multiple processes running, for example, and if you pinpointed that specific CUDA kernels might be the problem or your performance problem that you need to solve, then you could use Nsight Compute to further dig into that. If you would work on a graphics application like a DirectX, Vulkan, OpenGL, you would also start with Nsight Systems, and if you find that a certain shader is the problem, for example, then you could continue with Nsight Graphics to profile and debug that. So a few introductory slides about Nsight Compute. Nsight Compute is a CUDA kernel profiler. It has targeted metric sections for various performance aspects, and I'll be showing more about that later on. It's very customizable in terms of data collection and data presentation. So especially in the UI, a lot of the things that you see can be customized. You have predefined curated sets of things that can be collected, but you can also adapt them or extend them as necessary. There is a UI on Linux, Windows, and macOS, and there's a command line on these platforms and many more. And you can collect data via both or a combination. And last but not least, there are Python-based rules for guided analysis or post-processing of your data. So if you're familiar with Visual Profiler, they had this expert system. And this is kind of the successor to that, where you can get further expert analysis about your metrics. There's detailed memory workload analysis chart and tables that show you exactly which data or which number of requests are transferred between each of your memory units in your GPU. It supports comparison of results directly within the tool, using what we call baselines. So you can select one or more results as baselines, even across reports, across kernels, across GPU architectures, and then compare what you currently see against those baselines. There is a very helpful source analysis and source correlation support. With source, I mean here like high-level CUDA-C, OpenACC source that you would probably write your application in or your kernel. And then depending on how your kernel is compiled, that can be correlated to PTX and or SAS. and we can collect several metrics on a instruction level basis, so per source line, so to speak. For example, PC sampling data, which is shown in this screenshot, and which can be very useful to pinpoint where exactly in your source, which instruction, which line might be the culprit of performance issue. And on the right-hand side, there's a heat map of the currently selected metric to show you if your source is larger, where exactly are the values high, where are the values low, and you can quickly jump there to investigate. As I said, besides the UI, there's a full command line interface for data collection and analysis, which you can obviously use on your local workstation, but you might need to use if you run in a cluster environment where you only have a batch system and don't have interactive access to the profiler. And you can collect the data via the command line interface, but you can also directly analyze it. So you don't, if you work on your Linux cluster, you don't necessarily have to get the reports off there to your Windows laptop, but you can inspect them as well. The analysis support is a little bit more comprehensive in the UI, and it might be more convenient for certain aspects, but a lot of the data is also there available directly from the command line interface. Okay, yeah, I already mentioned Nsight Compute on your cluster. So working in a cluster environment, as you probably know, there are a couple of restrictions or a couple of things you need to think about. For example, how do you analyze the data, right? So by default, the command line results are printed to standard out, as with most Linux tools, I guess. But you can also use the export option to save it to a report file. So that's not a text file, but a binary format that you can then load in another CLI instance later or load in the UI. And if you want to write to the same file again and again, then you need to use the -f, the force option, to allow the tool to overwrite the existing file. There's also the --log file option, where you can pipe text outputs to a different stream. So if you don't want to store it in this binary file, but instead of printing it to standard out, print it to standard error, for example, because you want to separate the Nsight Compute output from your application output better, then you can use this option. You can also use environment variables and placeholders in your report names. And there are a couple of examples shown in the next two lines, which is a feature that came originally from nvprof, the predecessor of Nsight Compute, and which had support for putting these placeholders for the process ID, host name, environment variables, or just an incrementing number in your report name. And then you can generate, for example, a uniquely named report file every run, or have a report file that is named according to your MPI rank, for example. And I also put a link here, and I have these links in a couple of my slides for further reference if you want to read about this feature, how to use it. So Mohsin, I have a question. How do we want to handle questions? Do you prefer it to be at the end, or do you want to allow questions in between as well?
So every attendee has a Q&A box. And I would invite all the attendees to write their questions if they have any. And what we can do is we can read it later and then answer them.
Yeah, that makes sense. Okay? Sounds good. Sure. Thank you. Okay. Yeah, continuing on the cluster part. Obviously, if you run your application on a cluster, you often have a multi-process application, one that uses MPI, for example. So there are a couple of things to think about in terms of which combinations can be supported, and how would you set up your profiling job to adequately cover those. So most trivial one, on a single node submission, Nsight Compute can profile all launch processes. Or to be more precise, all processes launched by a single root process, the MPI launcher, for example. And if you set it up this way, then data for all processes is stored in one report file. And by default, Nsight Compute only profiles the first process that is launched. Like if you do NCU MPI run, for example, then it would only profile the MPI run executable, which is likely not what you want. But instead, you would have to use the -- target processes all option, and then it follows the process tree and can collect the data from all processes into a single report file. Okay. On multi-node submissions, if your job runs on multiple nodes, one tool instance can be used per node, obviously. And the only thing you have to make sure is to ensure that these instances of Nsight Compute don't write to the same report file. Because if they run on different nodes, they don't know anything about each other. So there can easily be conflicts or corrupted data if you have them write to the same file on a shared file system. And one way that is commonly solved is to use one of these placeholders that I mentioned already, in this case %q. And then let's say you have an open MPI application, you could put your MPI word rank there, and then that would make your report files named uniquely. Multiple tool instances on the same node are supported, but there are a few caveats to that. So assume that you have a multi-node job where two ranks would run on the same node, right? In that case, for example, then as with all concurrent profiling of different Nsight Compute instances on a single system, all kernels across all GPUs will be serialized using a system-wide file log. And that's to ensure that certain restrictions in the driver and in the hardware are not violated, because that would just cause errors and crashes. So there's only a single performance monitor instance, for example, in the driver. And the tool has to make sure that if you run multiple Nsight Compute instances on the same system, on the same driver instance, then these don't try to acquire this performance monitor at the same time, because that would fail. And the way that's handled is we have the system-wide file log in your temporary directory, and all kernel launches are simply serialized so that they try to acquire the file log one after the other. There is a bug in the current implementation of this file log related to permissions on it, which has the effect that all instances must be of the same user or have full permissions on this file. And by full permissions, I mean permissions to actually change the permissions. That is fixed in the upcoming version, where the permissions are set properly automatically. But if you run on a shared cluster where there are multiple users right now, you might need to be aware of that. And then you might just want to consider profiling only a single rank using something like a wrapper script. For example, because all your ranks do the same compute, right? They run on the same kind of style of data, on the same type of GPUs, have the same workload. So just to not consume as much disk space and make the analysis later easier, you might just want to profile only, in this case, rank 3 of this MPI job. And then if you can just wrap your launcher script in another script that only prefixes the job with Nsight Compute if that's a certain rank. Okay, now that we have collected all this data on our cluster, we need to retrieve it for further analysis. And as I said, you can use the command line NCU for that to import and analyze directly on the node or on your front-end node. But more commonly, I would say, is to transfer the report to your local workstation, where you can use the UI for more comprehensive analysis. The reports we currently generate compress very well. So if you have a large report, consider just compressing it before transfer in case you have a slow connection. And reports can be analyzed in any host system. So you can collect your data on Linux cluster or PowerPC cluster and then open it on your Mac or Windows UI. That works as well. Yeah, and as I said, the UI is a little bit more comprehensive and user-friendly probably. The CLI can be more easily automated. Like you can, all the output can be generated as CSV format, which makes it easier to export it to Python or JSON or Excel, or what you want. Okay, so then the next question is probably, what do we want to collect? As said in the beginning, it's relatively customizable. So there are a lot of options, and sometimes it's a little tricky to know what to choose from if you're not a expert performance analyst, I would say, or an expert tool user. So what we came up with are these curated sets of what we call sets and sections, with very commonly used and what we think high-value metrics. So metrics that make sense to a lot of users in a lot of use cases. And a section is a kind of a logical domain, for example, very high-level speed of light, or compute analysis, memory workload analysis, warp scheduler analysis, occupancy. Those are different sections that we provide. And in each section, we have a few metrics that map to this logical domain and that we think make sense to collect together. And to make the process even a little bit more easy, we decided to use what's called sets of sections. So sets in this case, in the example here, are default, detailed, full, or source. And the default set is just what is being collected if you don't specify anything else. And if you already know that you need more information than that, or that your profile time is very scarce and you have to make most of your single run, then you could, for example, use the full set, or a combination of different sections if you know what you're looking for. But one thing to keep in mind is that the more you try to collect, the higher the overhead. And that can increase your profile time quite a bit, depending on how your application is structured and what your kernels are doing and which exact metrics you're trying to collect. And on the bottom of the slide, you see an example use. For example, use the default set, but then also add the source counter section and add this one metric that collects how many instructions use the tensor core pipe. So you can combine them as you like. If you want to specify individual metrics, like in this example, then you might need to look up which metrics are available first. One good way to look them up is to use those section files, because as I said, right, we decided already that those are high-value metrics, and they also have very user-friendly names. But you can also query the existing metrics that the tool supports using the command line and using the -- query metrics flag. And you can do that on the local system if you have a GPU and a driver, but you can also do it offline on any host by specifying the target chip. And then you will get a list of base metric names with their descriptions. And if you want to collect the metric from the command line, then you can just put the space metric name there, and it will collect all submetrics. If you want to put it in a section file, then you have to specify the exact submetrics that you want to use. And submetrics are something shown on the bottom of the slide again. So for example, for SMINT executed pipe tensor, there are some average, min, and max, and others available. And the documentation also has more info on what these submetrics mean in detail. Okay, I already spoke about source analysis. So the SAS, which is the assembly, like your Kubin, is always available in the report because we embed it. And the CUDA-C, like the high-level source, and PTX availability depends on the compilation flags. So to have this correlation between your SAS and your high-level CUDA-C, you need to use the -line info option or the debug option during compilation. And in that case, then you have the correlation information embedded in the QBin. And to actually see what it's correlated to, you also need to have the high-level source available somewhere so that the tool can just open the file for you. Because the source is not embedded in the report by default, but need to be resolved via some kind of local or SSH access. However, the next version will give you the option to import the source directly so that it's permanently embedded, which can make it a lot easier to do side-by-side comparisons of optimizations of the same kernel, or just send the report as a single unit to somebody else for analysis. And another thing to keep in mind is that compiler optimizations can prevent exact source SAS correlation. So this is nothing that kind of the tool has control over. It's completely up to the compiler to do that. And if you very aggressively optimize your code, then, which obviously is something that you want for performance analysis, but then sometimes your instructions might be associated with a closing bracket or something, because the compiler optimized a lot of stuff away. Okay, here are just a few example screenshots how this can look in the UI. On the source page on the very left, there is no line info, so only the SAS view is available. In the middle, the application was compiled with -line info, but the source is unresolved at the moment. So the tool doesn't know where to find the CUDA files. And on the right-hand side, the source is then resolved, and you have the correlation between the high level and the low level. Okay. So some of you might already be familiar with the predecessor tool, nvprof, which is being deprecated for profiling metrics. But to simplify the transition between nvprof and Nsight Compute and Visual Profiler and Nsight Compute, we have these transition guides in the documentation and also blog posts on that, which I recommend to read if you want to know what exact options are available, matching, or which metric names of the new tool match to the old tool. Some other differences to keep in mind, besides the different metric names, is that flushing the caches and controlling the GPU clocks is enabled by default in Nsight Compute for more deterministic data collection, especially if you have a kernel replay, and that the tool is much more customizable. But on the other hand, some things that are missing so far is, for example, NVLink metrics or MPS support. And trace is kind of missing by design because there's a new tool for that called Nsight Systems that I spoke about in the beginning, which is much better for tracing the application and for seeing the API calls or kernel calls over time. Okay, so much for the general introduction explanation part. Then I want to go in two examples. One is Gromex that we profiled, Gromex 2020, and there are two kernels that were analyzed and optimized here called PME, Spread, and Gather. And I first go over the old version and then explain the optimization and how that can be inferred from the tool, and then we briefly look at the new version of those as well. Okay, and just about the kernel, so this spread or spline and spread kernel is used to spread data across different clients, different ranks, and the gather kernel is then the opposite operation and gathers this data from multiple ranks and uses it or transforms it for the local rank. Okay, and for the first one, I actually want to show that live in tool. Can you guys see the UI?
Yes.
Yes.
Okay, perfect. Okay, so I opened the report already, the old one in UI, and brief overview what we see here on the report. We have different pages, and by default, we start on what's called the details page. And then we have this launch drop-down where we can see all the kernels that were profiled, all the different results. And I have the first one I have currently selected, and that's what the data is for. If I would select a different one, this data would look different. And in this header here, I see some overview information about this kernel. The name, its grid size, how long did it run, how many cycles, what kind of GPU was it on, in this case a V100, and so forth. And then we have these different sections, which are those logical domains: speed of flight, compute workload, memory workload, and so forth. And we can open these to get more information besides this overview header. And they are roughly structured from high level to low level. So it makes sense to start on the top and then drill down from there. So often you will see these recommendations. And then these recommendations will tell you what further sections to look at, or what we think would be a good optimization or a good thing to look into, for example. But yeah, looking at the overall high-level performance of this kernel, we can see how much it utilizes the compute units of the hardware and how much it utilizes the memory units. And we see that the compute or SM utilization is fairly low with 20%. The memory utilization is a lot higher, not bad actually, around 50%. It's not, the goal is not to get 100% for both, right? Because it doesn't show you how efficient you're using the hardware. It only shows you how much you're utilizing the hardware. However, if you have a very low utilization and you expect the hardware to be somewhat utilized, then likely you're not using it very efficiently. If you have extremely high utilization, that means those units can become a bottleneck, right? The hardware might become stalled and would like to issue more work, but can't at the moment. Okay, and yeah, looking at the recommendation, the tool says there's slow compute throughput and memory bandwidth utilization relative to the peak performance of this device, because both are below 60%, and that's typically a latency issue. And then it recommends to look at two other sections: scheduler statistics and warp state statistics. This is a slightly older report. If you had a newer report, you can directly click on those. There are links, and you would go there. In this report, you have to manually go to the statistics or to another section. Okay, let me briefly go back here. This is kind of the same screenshot that we just talked about. Going through, instead of only looking at the recommended sections, I want to look at most sections, I believe, just to give you a better idea what's in each section in this presentation. So in the compute workload analysis section, we see that the highest utilized pipeline is called LSU, the load store unit, indicating a high load of memory load store operations. If you hover over this, there's a little description, but in the documentation online, in the kernel profiling guide, there's even more detailed description of what these units mean, which instructions may be in which unit or in which pipeline, things like that. Okay, but here we have a high load of memory load store operations. Looking at the memory chart, it shows that stores are much more common in this kernel. So what we see on the very left-hand side, we have kind of the kernel, the SM, and then we have all these logical memory spaces that our SM could issue instructions to. And those instructions are then converted to requests. to specific caches, for example, or to shared memory. So the L1 cache or shared memory. And then from the L1 cache, the request might need to go further up the hierarchy to L2 cache or even to device or system memory. And what we see here is that there are a lot of global instructions accessing global memory. There are also a lot accessing shared memory. But the number of requests to store is a lot higher than the number of requests for loads, which then results in a lot of like stored traffic from L1 to L2 and to device memory, but not the other way around. But we already know that our bandwidth is not saturated, right? We're only at 50%. So it's likely the frequent operations that are the problem and not the bandwidth that those operations generate. Looking at this recommended section, the scheduler statistics, we see that we have many active warps available. So you see the number of theoretical warps, which are the optimum of 16 here. And the active ones are pretty high at 13. But they are not eligible, meaning even the scheduler, if the scheduler would try to issue them, they aren't ready. They aren't available because there's some stall reason that prevents them. And that's then split out in further detail in the next section that was recommended, these warp state statistics. Oh yeah, and by the way, I mean, these recommendations give you a lot more detail than what I'm explaining now to understand what's shown here better. So this warp state statistics section then shows us, okay, why are these warps stalled? Why can't they issue instructions? And in this chart, we see the stall reasons and the number of cycles per instruction on average over the whole runtime of the kernel that warps were stalled. And we can see that the biggest impacting stall reason are the LG throttles, so the local global throttle stalls, that on average stalled our warp 30 cycles per instruction. Right, so the ideal issue is one instruction per cycle. So there was like a 30x overhead in certain cases. And looking up the documentation for the LG throttles, it would show us that this indicates extremely frequent memory instructions, which is also explained in the rule below. And so we already know we have a lot of store instructions that are problematic. And now we can use the source page to find out where in our kernel are these instructions coming from. And for that, let me go back to the tool and let me switch from the details to the source page. And in this case, I have line info and I have my source resolved. So I have the high-level source on the left and low-level source, like the SAS assembly on the right-hand side. And I want to look for a specific problem. I want to look for these LG stalls, LG throttle stalls. So I can select this metric for further navigation. And then the heat map is updated accordingly. And I can also use these navigation buttons to quickly jump to the highest source line or the lowest source line with that metric value. And I first go to the, let me change that to better show the sampling data. There we go. I first go to the line with the highest number of throttles, but this is in our in the very beginning of the kernel where we are actually loading. So this is not the one we're interested in. And I go to the next lower one, which still has a high number of 280 stalls or samples here. And 80% of these samples are composed of LG throttle stalls. And what we can see here is that the data that this kernel computed, part of the data that this kernel computed, is written to global memory. You can see this right global condition here. That's because the kernel is already kind of the optimized one with the optimization disabled. And we kind of use the same source in old and new just to make it easier. But yeah, we see okay, so if we could avoid writing this data to global memory somehow, then this might be beneficial. But it also implies that, I mean, it's written to global memory for some reason, right? To be picked up by another kernel. And this implies that this other kernel, which is the scattered kernel that I mentioned in the beginning, then has to recompute this data. So it's not completely free to avoid this, right? Okay, quickly going over the old version of the gather kernel in less detail. We see there's more balanced compute memory utilization, but still it's slightly latency bound, which is what tool is telling us. It reads this temporary data that this spline and spread kernel wrote to global memory. And logically, we have a lot more data being loaded from device memory and coming from a lot more load requests and load instructions than stores. The biggest store reason, or the biggest contributing store reason here are long scoreboards, which indicate waiting on local or global memory to be loaded, which again makes sense, right? We're mostly loading here. So it makes sense that this would be our biggest contributor. And it also shows that they're not loading ideally, right? We don't have enough concurrency, for example, to hide the latency of loading this data. Okay, so looking into the optimization, right? I mean, I'm not going to do the optimization here. That was done by the application expert in this case. But the idea was to not write this temporary data to global memory and then read it again from the gather kernel, but instead recompute it in the gather kernel. Because we saw in the beginning, our compute units are not very utilized, so there's a lot of headroom to add more compute and remove this memory latency. There was also a second optimization done in the same submission here, but it's not activated in this analysis. Okay, yeah, looking into the new version. So I collected a result for the new version of this spline and spread kernel. And to nicely diff them between the old and the new, I can go to the old one and select Add Baseline, which adds the current result that I'm currently looking at as a baseline for all further comparison. And if I then go to the new kernel or new result, I can see that all my current data is diffed against this baseline. So I could also rename this to old, for example. So the blue one, the current one, is the new one, and the green one is the old one. And we can see already from the summary, it got faster, right? We dropped from 83,000 cycles to about 69,000 cycles. The actual delta therefore is about 15%. So the kernel got 15% faster, and we utilize memory a little less, but instead have a little more compute utilization, which makes sense. We're writing less data to memory, so our memory pipelines are less utilized. And yeah, we can these 15% performance improvement most likely come from the much reduced DRAM throughput, or much reduced DRAM utilization, which is down by about 50%. Yeah, so less utilization of the load store pipeline, but increased utilization of the arithmetic pipelines, which is probably good, since you want to compute something in this kernel, right? It's not for transferring memory, it's for computing. So if you have higher utilization of your arithmetic pipelines like ALU or FMA, that's probably a good thing. As expected, we have much reduced global store requests. They are down by 70%, and the loaded data, the written data is down by about 75% even, because we're not writing this temporary data anymore. The eligible and issued warps per scheduler in our scheduler analysis improved slightly, but not a lot, to be honest. So there's still headroom for optimization, right? I mean, ideally, we would issue one warp every cycle, and we are at 0.25 cycles, so we only issue every 4 cycles, and yeah, could do a lot better. But that would require further analysis and further optimization. As expected, we see that these LG throttle stalls are down a lot, since we have fewer writes to memory. And yeah, so overall, nice improvement. Looking at the gather kernel, which now, as we explained, has to do the recompute this data instead of loading it for global memory, we see that the performance actually decreases slightly compared to the previous version. So the kernel got about 20% slower because it has just more cycles elapsed. It also has a lot less DRAM throughput because it loads less data, but it has higher SM throughput because it now has to recompute these things that were previously already available in memory. And yeah, we could further analyze why exactly it changed the way it changed. But overall, the thing that interests us is that these spread and gather kernels always occur in tandem in our application. So we need to look at the sum of the runtimes of both, right? And good for us, the accumulated runtime decreased by about 10%, because this spline and spread kernel that got faster was kind of the higher contributor, and the gather kernel, which was not as long in the beginning or to start with, this slight decrease in performance didn't matter too much. And what's showing here is the summary page. So if I would go back here, there are more pages that can be looked at. Summary page that gives an overview about just all the kernels that were collected, and their device, their cycles, and memory and SM utilization, kind of like the super high level metrics. But there's also a raw page which simply has every metric that was collected for every result. And you can transpose these pages, because depending on if you're looking at metrics, more metrics or more kernels, one might be more interesting than the other. But yeah, then it would allow you to have a very detailed view at a specific metric. And I believe I think you need to actually, yeah, you can filter them as well over here. Like if you only look for a specific device attribute, then you could look this up more quickly by typing in this filter box. Okay. All right. Besides Chromex, another example I want to go over is an image feature extraction kernel for where I can present something called Roofline Analysis. Okay. So what this extract features kernel does is it originates from our last GTC slab content, and it analyzes an image for interesting pixels by a certain feature extraction algorithm. And part of the algorithm, or part of the preparation work for this algorithm, is to convert the pixel color format from color to grayscale in this case. And what we can see from the Nsight Compute analysis is that the kernel is heavily compute bound, utilizing the SM units more than 80%. And we can also see from this breakdown below that, where we see, okay, what are the contributors to the SM speed of light and the memory speed of light utilization? we can see that what makes the SM units 80% or over 80% utilized is the 64-bit floating point pipeline utilization, called FP64 pipe, being with 86% the highest contributor. So the way these SOL metrics work is that they just pick the max contributor of their individual breakdowns. And since we're talking about floating point performance now, and floating point analysis, there's a relatively new feature called Roofline Analysis, which can help in understanding how close are we to the theoretical peak, and are we more compute bound or are we more memory bound with our floating point usage. So what we see here is in this chart is that we have what looks kind of like a roof, right? This diagonal line and then these two horizontal lines. And we have two horizontal lines here because there are two peaks, one for 32-bit floating point on the top and one for 64-bit floating point, double floating point a little below. And the reason why they are so far apart on this logarithmic scale is because the GPU this was measured on, the Turing 2080 Ti, has 32 times the 32-bit floating point performance as it has 64-bit floating point performance. On V100, on Volta, the ratio would be less. It would only be 2 to 1, 2 times as many 32-bit FP units than 64-bit FP units. And then we see how much we achieved in terms of 32 and 64-bit performance. And we can see that the 64-bit, which we know is our kind of pipeline limiter, is already very close to its roofline. Like, it's very close to its theoretical or hardware limit, while the 32-bit one is very far away. It's even in the memory-bound region and not in the compute-bound region of the roofline. And knowing that, I'll try to skip already here. And knowing that, we might want to figure out, okay, where do those 64-bit floating point operations come from in our source? And for that, in this report, I'm first clearing the old Gromix baseline because it's not relevant here. We can look at the source page, put that over here to make it easier. And we can try to find out, okay, where do these instructions come from? And for that, let me filter this a little bit. And then I select instructions executed as the metric I want to navigate by, and go to the place in my source where most instructions are executed. And jumping there, I see, okay, it's in this utility function called RGB to luminance or RGB to grayscale, which does the color format conversion. And then if you select this, as it's done here already, on the high level, you see on the right-hand side in light blue all the instructions that the compiler generated from this high-level line, kind of with this blue background. And we can see there are a lot of 64-bit floating point instructions, converting from integer to floating point, or logic operations on 64-bit, or double precision multiplications, or fuse multipliers. Okay. Yeah, knowing our algorithm, we're not doing like super complex math here, right? We're just converting a color to grayscale. And for that, we likely don't need 64-bit precision. It's completely fine to just use 32-bit precision, especially since we have so much more 32-bit units available. And we can simply change the kernel to convert or do all the operations in 32-bit. And then we get a great performance improvement. So if we do the comparison again, we see, okay, it's about even 90% faster in this case. we have better memory utilization because we're not stalled as much by these floating point operations. And we can see that the FP64 pipeline is now not a contributor at all anymore. It's 100% as contributing because there are simply no 64-bit mass operations anymore. Okay, a few links for further reading on this is the Roofline part of the profiling guide, this GTC lab training that I mentioned, or from NERSC, a good tutorial and content on Roofline analysis on NVIDIA GPUs. Okay, so much for the examples. Wrapping up more or less, I want to go through some, a little more advanced topics maybe, like customization or customizing data collection and analysis. I already mentioned that the tool is very customizable, and this is true for both data collection and both for presentation of the data. And one of the most customizable or things that you would probably want to look into for adapting the tool to your needs are those sections, which are simply text files, Google protocol buffer text files, which have a certain format and then define, besides the name and the description and the sets they belong to, which metrics should be collected as part of this section, and what are the names the UI should show for these metrics. And if you have a specific need, like, okay, you always need these 10 metrics and you want them in a specific chart in the UI, you can just write a little section file, a little text file, and add this to your tool, and then collect this specific section file instead of having to type the individual metrics every time. And very similarly for these recommendations for the rules, those are little Python scripts that have a specific API called the nvrules API, which is also explained in the online documentation. And they can be both interesting for you to read which metrics feed into this recommendation and what are the thresholds or what is the kind of decision tree leading to this recommendation, or to adapt or add to your needs, right? If you have a specific analysis that you want to do for your metrics, then you can write a little Python script and get the recommendation directly in the tool every time. But you can also use it to just understand, okay, why do we think this is, at which threshold this metric is a problem, and why do we think this is latency bound versus compute or memory bound, for example. Yeah, and as I said, there's also a customization guide and an nvrules API documentation online. Okay, yeah, wrapping up. Of course, there are known issues, right? Go to the online docs release notes to see what has changed in each version, which GPUs and platforms are supported, but also to see which known issues are there. And in the profiling guide, there's also an FAQ section recently on what are potential workarounds, for example. A little outlook for the next version that's coming. Features that we're adding are the source import, to import the high-level source directly in your report file. Couple of Roofline analysis improvements to make that more convenient and to have a nicer UI, I would say. Source level divergence metrics. So divergence metrics was something that was available with nvprof and now is coming back again with Nsight Compute. And also something that we call profile series experiments, where in certain bounds or ranges, you can have tool change the occupancy of the kernel by allocating more shared memory or using more registers, and try to understand, okay, how would my performance change if I would use more or less shared memory, or how would it change if my kernel would require more registers? Would my occupancy go up or down, or how does the performance look. And some of these changes the tool can do automatically and then provide you with a series of the results. Yeah, and just concluding, so Nsight Compute enables detailed kernel, CUDA kernel level analysis. Rules give guidance on optimization opportunities and help you understand the metrics that the tool collects. Try to limit the sections of metrics to what is required when overhead is a concern. If you're using a recent version of the tool, also think about using application replay instead of kernel replay. So what that means is that when not all metrics can be collected in a single run of the kernel because there are certain hardware limits or because metrics can't be collected with each other. And in that case, the tool replays the kernel multiple times to collect a specific batch of metrics in each pass, in each replay pass. And to have a deterministic execution of this kernel every time, we have this clock control and cache control that I mentioned. But we also have to save and restore the memory that is accessed by the kernel because the kernel needs to operate on the same input data every time. And this memory obviously needs to be saved somewhere. And if we have space in device memory, then we save it there. If we don't have space in device memory, we have to put it to system memory, and even that might not be enough in certain circumstances, and then we have to back it up to file, which obviously would be very slow. It can be problematic, especially if your kernel, like you have a large GPU, like an A100 with a lot of RAM, but much less host memory. And one way to resolve this can be to use application replay, where not the kernel is replayed, but the whole application is replayed for each pass. So a specific set or batch of metrics is collected in each application pass, and then the whole application is restarted, and the next batch of metrics are collected. Of course, that requires that your application is deterministic in certain bounds, but it means that no memory needs to be saved or restored. And it also means that certain unified memory interactions between the host and device can be profiled, which aren't available to be profiled with kernel replay. But yeah, even though we have all these recommendations and everything, there's still a level of hardware understanding required to fully utilize the tool. And this online profiling guide tries to give you some guidance and some hints on to better understand this. Okay, yeah, just a few links to the forum where you can also ask questions or look what other people asked, as well as a couple of training videos and blogs. And with that, I'm done. And let me try to see if I can reload this here.
Right. So I guess there are a couple of questions in the Q&A box, and there is one in chat box as well. So should I read it for you, Felix?
Yeah, I'll have the Q&A open. Let me see. When you say source analysis, slide 18, what type of source code analysis is performed by Nsight Compute? Is it just mapping the profile and performance information to source code line numbers? Pretty much, yes. So there's no static analysis on the source code, especially not on the high-level source code. There is some static analysis performed on the assembly, and one result of the static analysis is, for example, this live register information. Let me try and get this a little bit out of the way, where we use the disassembler to show you how many live register or how many registers the compiler needs to keep live for each instruction. And that can help if you are register bound or you want to optimize for using fewer or more registers to understand which part of the source code requires that many registers, right? Or would contribute to spills into local memory, for example. But there's no analysis in the sense that we try to understand what the kernel is doing, things like that. So yes, it's mostly about correlation line numbers and static assembly analysis. Another question, our team uses more command line tools and run on a server. We are familiar with tools such as NVTX. Do the guys support monitoring and remote job? In addition, are there specific tools available for TensorFlow other than what we mentioned? Yeah, I mean, this appears to be multiple questions. So there is support for NVTX. NVTX is the NVIDIA tools extensions, which is a markup language that you would add in your C++ or Python code, and which would then show, provide more domain information from the application to the tools. For example, in Nsight systems, you could have those ranges, NVTX ranges, to see, okay, this kernel was in my innermost loop, or this kernel was in my preparation phase or my exit phase of the application. And Nsight Compute can also collect this, NVTX information. You just have to use the --NVTX flag, and then allows you to, for example, filter to see, okay, I only want to see kernels that are in a specific NVTX context. I only want to see kernels that have the preparation phase range on the call stack already during collection of the data, for example. Or I want to turn on profiling at a later point. And it also shows you, like, if you have further payloads like resources, can show you that there's a specific NVTX page, or there's even NVTX information. Yeah, so this kernel, for example, had 3 NVTX ranges in the default domain, and they were push-pop ranges, so they were local to the current thread. And we can see that we were in the compute features database part of the application, processing an image, and within processing image, we are running the kernels. Does the UI support monitoring and remote job? That depends what you mean with monitoring. So Nsight Compute can only profile applications that were launched via Nsight Compute. So you can't just profile a random application or an application that's already running. We do support remote launching and remote attach in both interactive and non-interactive sessions. So in an interactive session, you can add, you can select your target platform. For example, I'm on Windows, but I want to profile on Linux. And then you could enter your connection details. And in certain configurations, you can remote launch. Like if you have a Linux target, you can directly from Windows say, okay, launch this remote job. If you have a Windows target, then we can't remote launch, but you would have to launch via the Nsight Compute CLI in a certain launch mode, which is explained in the documentation. And then you could attach, which is currently disabled here. Yeah, because I can't select this in this setting. You could attach to this remote job. In addition, are there specific tools available for TensorFlow other than what we mentioned? Yes, there are more tools for TensorFlow or deep learning analysis. I believe there's a TensorFlow tool itself from Google, TensorBoard, I'd say. Don't pin me on that. There's also nvprof from NVIDIA, which allows you to analyze your tensor or your DL application more on a model level. And then there are also specific, for certain domains, there are also other AI tools from NVIDIA called, for example, the Feature Map Explorer, which we recently released to allow you to debug or profile certain layers of your models. Okay, what do you mean with eligible verbs? Does this mean the occupancy related to the active verbs within this? No, so occupancy and verb eligibility are 2 different things. So occupancy means how many blocks or how many verbs can be resident on an SM at the same time. So each warp or each block requires a certain set of resources like shared memory, registers, and so on. And let's assume your SM has 48 kilobytes of shared memory, and each block requires 20 kilobytes. Then you can only have 2 blocks resident on the SM at the same time. That's your occupancy, and it can be good to have high occupancy, or that's your occupancy limiter, right? And then let's say you have 20 SMs, then maybe you can occupy all your SMs with blocks at the same time. If you have only 10 blocks, then you can only occupy 10 SMs, so you have only 50% theoretical occupancy. So there are a lot of variables to that. And it can be good to have a high occupancy. Normally that's good, because it means you're utilizing the hardware resources better. If you have a very specific type of problem where you need a lot of memory bandwidth, for example, then it might, or you need a lot of registers, then it might be better to have lower occupancy, but use more registers for your kernel so it doesn't spill to local memory, or so that each warp can utilize the full memory bandwidth. And so there's an occupancy section that in the details page, if you collect it, that gives you more information on that. It also gives you the charts where you are currently on these varying parameters. Or you can use, in the newer tool, you will be able to use this profile series experiments feature to do some of these experiments automatically, right? Would I benefit from lower or higher occupancy? And then warp eligibility is more, is a scheduling and a latency problem. So, yeah, I might necessarily try to get this out of the way. I can't make this smaller, that is great too. Yeah, I'll just make my life easy and just read the recommendation to you. Every scheduler is capable of issuing 1 instruction per cycle, but for this kernel, each scheduler only issues an instruction every 24 cycles. This might leave hardware resources underutilized and might lead to less optimal performance. Out of the maximum of 8 warps per scheduler, this kernel allocates an average of 6 active warps per scheduler, but only an average of 0.1 warps per eligible per cycle. Eligible warps are the subset of active warps that are ready to issue their next instruction. Every cycle with no eligible warp results in no instruction being issued, and the issue slot remains unused. To increase the number of eligible warps, either increase the number of active warps or reduce the time the active warps are stored. So ideally you wanna issue an instruction every cycle just to keep the pipeline fat. But if you have stall reasons, or if you don't have enough instructions or not enough parallelism, then those might be contributors why the scheduler is not able to issue an instruction every cycle, and those hardware resources will go wasted. Okay, that's all the questions I can see, I think.
Yes, fabulous. Thanks a lot, Felix. There's one other question in chat box. Is there a DLI course for Nsight Compute?
I think there's no specific DLI course for Nsight Compute. The reason being that often it might not be the ideal tool for the job. So a lot of times if you do machine learning or deep learning, you're not writing custom kernels, but you're using like an existing framework like PyTorch, TensorFlow, on top of other libraries like cuDNN, for example, or like a framework like TensorRT. And in those scenarios, you often don't have explicit control over your kernels, right? You can't make a change to say, oh, I want to change the source code of this kernel, or I want to change the number of registers. It's all decided for you by the library or the framework. So you can still profile these applications, of course, right? On a CUDA level, you can definitely profile them, and it might be interesting to know. It might be interesting to understand which parameters you might want to tweak if you have those parameters. But often it's too far away, right? It's a very low hardware level, while you might be working on a very high-level abstract Python level. And that's why there are other tools that try to fill this gap in between, like nvprof or maybe better Nsight systems. So there's no specific DLI course. I mean, I assume the question meant DLI course specific to deep learning.
Yeah.
Okay. There will be likely courses coming with the next GTC. Those will likely be about artificial intelligence or deep learning as well. And they will likely be provided via the DLI infrastructure. But yeah, depending on what your scenario is, it might be what you're looking for.
So we should probably expect a nvprof course rather than Nsight Compute course.
You're right. If that is your, like, if you're really trying to optimize your layers in your model or your inference, then yes, I think there are nvprof courses.
Sure.
Yeah, I would have to look it up.
So I have a question about the NVLink traffic and nickel tracing. Is there a possibility of doing it in any of the tools in the suite, or what do we do about this?
Yeah, I think unfortunately currently it is not. There is no. It was available with nvprof, but I think on recent GPUs, on MPA GPUs at least, you won't be able, or Turing even, you won't be able to collect those metrics from nvprof. And that's one thing I mentioned in the what's missing, right? The NVLink metrics are currently missing from Nsight Compute, even though we are in the process of adding them, we just didn't get there yet.
So
and I believe the same is true for Nsight systems.
So they will be captured from, let's say, NVIDIA SMI's NVLink subtool. Is that where it will be captured from, or are you going lower level to do something else there?
So yeah, we will be using, we use this common metric library or metric collection library called Perforx.
Yeah, okay.
Yeah, called Perforx, which is also the basis for NVML, for example, or for the DCGM cluster monitoring tools. So all these tools build on this common Perforx library. And Nsight Compute uses this library directly. If you use something like NVML or DCGM, then it also uses this library directly. But it targets a different set of metrics, right? They only look for very low overhead, very non-intrusive metrics to kind of monitor, while Nsight Compute is a little more heavy-handed, depending on what you select, to give you like the most detail possible.
A related question, actually, there might be short ones. Can we export the graphs and the reports into something more portable, like a PNG or a PDF?
Yes, there's this button on most pages on the top right corner where you can copy what you currently see as an image, save it as an image, or save it as a PDF. For this page, for the table pages, like the raw page, you can also export it to CSV, for example.
Fantastic. And the last one would be something related to what you touched before. In terms of the GUI part, is there a way of doing a remote connection to the thing is actually running on the server and we control it from the GUI, but it is a reverse connection?
Right. Yeah, I think that's what somebody asked in the Q&A
yes.
already. Right. That's what you have. This connection dialog here, where you could add your connections, and you can also. There are two for the UI. There are two general modes. So for the command line, there's only traditional non-interactive profiling, right? You say, okay, give me these metrics for these kernels, write it to this report, and then fire off. For the UI, there is this mode as well. If you create a new session, it's the profile activity, but there's also the interactive profile activity. And what this does is it kind of more looks like a connection to your application, where you can then kind of step from API call to API call or from kernel to kernel, see all the parameters, decide which kernels to profile. You see all the resources that are active at this time, the current MBTX context. So it's very like an API debugger, where you can interactively step through your application or look at, if you use CUDA graphs, look at what the current graph structure is, how many graphs are there, things like that, or how much memory was allocated.
Fantastic. I think this is the last one that has just come in, not just come in, 10 minutes ago. How can we profile the execution of MIG feature of A100 GPUs in Nsight Compute?
Yeah, so Nsight Compute supports MIG on A100. There's not a lot of special setup required. One thing to note is that only one MIG instance can be profiled at a time on a hardware level. Normally, that is guaranteed by Nsight Compute already using this system-wide lock. If you kind of prevent that multiple Nsight Compute instances see the same temporary directory, then obviously this lock cannot work because it doesn't. These instances don't know of each other, and that might lead to problems like crashes or corrupted data. Yeah, mostly crashes actually. But yeah, MIG only supports profiling on a single instance. And then another thing to note is that depending on if your compute instance is a shared GPU instance or exclusive or isolated GPU instance, certain metrics are not available in shared instances because shared compute instances share like the DRAM with other instances, with another compute instance on the same GPU instance. And we can't allow you to profile these memory metrics of the shared hardware because you would be able to observe behavior of the other application, right? Which is likely not something that you want or that you should be able to. And there is information on this, on all these details in the kernel profiling guide under special configurations. There's a section on multi-instance GPU.
Superb. I think with this, we can now safely wrap up. Thanks a lot for your time and your expertise, Felix. We enjoyed a lot. And Sabir, do you want to close?
Yeah, no further points to add, except thanks a lot, Felix.
Yeah, you're welcome.
NVIDIA for all the fruitful and very productive tutorials and content, and hopefully that will benefit all our hackathoners right away and all our user base in the future. Thank you so much.
All right.
Thanks.
Yeah, thank you for having me. Bye.
Thank you. Bye-bye.
Bye.